This is the video lesson for Ohm's Law with series circuits. The learning target for this lesson is, I am learning to use Ohm's Law to solve real-life problems involving series circuits. The success criteria for this lesson are, I can calculate the equivalent resistance for the entire series circuit, I can calculate the current for a series circuit using Ohm's Law, and I can calculate the voltage drop across individual resistors in a series circuit using Ohm's Law. So what is a series circuit? How do we define one? So a series circuit is a circuit with only one path for the electricity to travel. So in a series circuit, there's only one way for the electricity to go. Current is the same across the entire circuit. So current I, it's the symbol we use for current, is the same across the entire circuit. So the current stays the same all the way through the circuit. The voltage, on the other hand, drops as it goes through each resistor. So any object on the circuit that resists the electricity flow, like a light bulb or a resistor, anything that uses up electricity as it goes, drops the voltage. We call that a voltage drop. Resistance adds across the entire circuit. So the resistance adds. So equivalent resistance is equal to the sum of all the resistors. So we can think about this thing called the equivalent resistance being the sum of all the resistors. So here we've got an talking about the equivalent resistance. So Req, so that's the resistance equivalent, or the equivalent resistance, is equal to R1 plus R2 plus R3 and so on. So if you add up the resistance of all the resistors together, that's going to give you the equivalent resistance for that circuit. All right, so let's talk about how we determine the equivalent resistance in a circuit. So again, we have the equation for equivalent resistance. So we have Req is equal to R1 plus R2 plus R3. So in this example, we have two resistors. We have a light bulb with a resistance of 10 ohms and another light bulb with a resistance of 5 ohms. So our equivalent resistance is going to equal 10 ohms plus 5 ohms. So in this circuit that we have here on the right, the equivalent resistance is 15 ohms. If we look at another example, example number 2, so we have resistor 1 is 15 ohms, resistor 2 is 7 ohms, resistor 3 is 20 ohms, and resistor 4 is 3 ohms. So our equivalent resistance is going to equal 15 plus 7 plus 20 plus 3. So our equivalent resistance is going to equal 15 plus 7 is 22, plus 20 is 42, plus 3 is 45 ohms. All right, so how do we use Ohm's law to determine the current? So remember, current is the same across the entire circuit. So current doesn't change no matter where you are in the circuit. That's true for a series circuit. So we're going to use Ohm's law with the voltage and the equivalent resistance for the circuit to determine the current in the circuit. So we use Ohm's law solved for a current, in this case, to figure out the current. So we have delta V, and we have divided by R. So this is the equivalent resistance for the circuit. So in this case, let's figure out the equivalent resistance first. So we have a light bulb with a resistance of 10 ohms and a light bulb with a resistance of 5 ohms. So we have 10 ohms plus 5 ohms equals 15 ohms. That's our equivalent resistance. And then our delta V is 6 volts. So it says right here on the battery, 6 volts. So at this point, at point A on the circuit, we have 6 volts. And after going through the batteries, the voltage drop is down to 0 volts. So our delta V is 6 volts. So our current then is equal to delta V, 6 volts, over our equivalent resistance, which is 15 ohms, which gives us a current of 0.4 amps. So anywhere we measure the current, anywhere along this circuit, if we measure the current here, here, or here, the current would always be 0.4 amps. All right, so let's talk about using Ohm's law to determine the voltage drop across each resistor. So we're going to figure out the voltage or the potential difference. So it decreases, the voltage decreases as it goes across a resistor. So that's why we call it a voltage drop. The voltage drops as it goes across a resistor. So we use Ohm's law with the current, which is the same everywhere in the circuit, and the resistance, so each individual resistance, to determine the voltage drop across that resistance or across that resistor. And we use the equation, standard Ohm's law equation, delta V equals I times R. So I is the current and R is the resistance of that particular resistor. So we know from the last time that we looked at this circuit that our current is 0.4 amps. We have our first light bulb, which is 10 ohms, and our second light bulb, which is 5 ohms. So those are the resistances. So between points A and B, we're going to have, so A to B, we're going to have a certain voltage drop. So let's figure out what it is. So our voltage drop from A to B, we have a current of 0.4 amps, and we have a resistance of 10 ohms. So our voltage drop from A to B is 4 volts. And then from C to D, we're going to have a voltage drop. So again, we have 0.4 amps times 5 ohms, which gives us 2 volts. So we can double check our voltage drop here. So our total voltage is 6 volts, and our voltage drop between our two resistors is 4 volts plus 2 volts. So that should equal the total voltage. So 4 plus 2 is equal to 6. So we're good. All right, so let's look at one example here where we put everything together. So we've got this circuit here, this series circuit with a 9-volt battery, and we've got 3 light bulbs, one with a resistance of 21 ohms, one with a resistance of 15 ohms, and one with a resistance of 9 ohms. So our first step is to figure out our equivalent resistance for the entire circuit. So we have 21 ohms plus 15 ohms plus 9 ohms. So that gives us a total resistance of 45 ohms for our equivalent resistance for this particular circuit. Next, we're going to calculate the current for this circuit. So our delta V for this circuit is 9 volts. So if we started at point A, we'd have 9 volts. And as we go through the entire circuit, we would be down to 0 volts. So our delta V is 9 volts. Our equivalent resistance is 45 ohms. So our current for this circuit is 0.2 amps. All right. And lastly, we're going to figure out the voltage drop for each individual resistor. Okay, so delta V is equal to I times R. So we're going to do from A to B. So that's our first light bulb. So our current is 0.2 times 21. That's going to give us a voltage drop of 4.2 volts. From B to C, it's going to be 0.2. That's our current, times 15 volts, or excuse me, 15 ohms. That gives us a voltage drop of 3 volts. And then finally, from C to D, our current is 0.2 amps, and our resistance is 9 ohms. So that gives us a voltage drop of 1.8 volts. Now let's just double check to make sure that everything adds up. So our voltage should be 9 volts. So we have 9 volts equals 4.2 volts plus 3 volts plus 1.8 volts. If we sum those together, 4.2 plus 3 is 7.2 plus 1.8 would be 9 volts. So everything checks out. So we have done a good job calculating the resistance, the current, and the voltage drop for each light bulb on this series circuit. Keep asking questions, everybody. It's how you learn new things.